last class we have discussed block diagram representation. So today first we solve two problems and then we'll start a new modeling technique that is called that signal flow graph. So block diagram representation. Block diagram representation. The first example is you have a plant here G1 and another plant here G2. One signal entering here, so this you have positive and that feedback is negative feedback. The feedback path gain is H1, transfer function H1. So in all cases those are G1 of S, G2 of S, H1 of S. And here you have that output YS. This is one summer plus, and here another signal is entering, that is DS. So now your objective is to find what is the transfer function from find transfer function YS by RS and YS by DS. So in this particular case, instead of deriving all the algebraic relationships, we will just write what is the transfer function, just looking at the forward path transfer function and that feedback path transfer function. So let us see first. So suppose that is YS by RS. So when we are finding YS by RS, so we assume that DS equal to 0. So then you can see here that RS is here and YS is here. So this is actually that forward path. So forward path transfer function, that is say G2 G1, and then at the feedback is negative, so that then that would be 1 plus. And in case of positive feedback, so if the feedback is positive, so here it would be negative. So 1 plus the forward path transfer function, that is G1 G2 G1, and that feedback transfer function is H1. So this is the transfer function. And in other case, whenever we will be finding that YS by DS. So YS by DS means in that case we will be assuming that RS equal to 0, but here this is not equal to 0. So in this case you can see that this is actually the forward path transfer function, that is G2, and here you can see this is actually that feedback path. This is actually feedback path. So this is feedback path. Now here you have that negative and here you have that positive. That means positive and negative, that is negative. So basically this feedback is negative feedback. So then you have 1 plus, and the feedback path gain is G1 to H1. So the so forward path transfer function is G2. So that is G2, and feedback path transfer function is G1 H1. So that is G1 H1. So this is the transfer function. So that means without just deriving all the algebraic equations, so just by looking at the block diagram you can write what is the transfer function whenever you have many signals, just by identifying which one is forward path and which one is feedback path. So this is the technique we normally follow. So let us solve another problem. So in this particular problem, you have many inputs and many outputs. So basically, we'll be finding one transfer function matrix that we have discussed in the last class. That means whenever you have multi inputs and multi outputs, in place of transfer function, we would say that this is transfer function matrix. So this is one example where we will be finding the transfer function matrix. And so this is a simple block diagram of a closed loop control system, and here you can see that noise entering at feedback path. So this is that noise. This is that noise, and here you have that GS. So suppose disturbance entering here, that is DS plus, suppose you are interested in what is that error signal here, ES, and this is that control input feeding to that plant, so that is US, and this is that measured output YS. So in this particular example, you have that reference command. So inputs are RS, then DS and eta S, and outputs are YS, ES and US. So we are interested in what is the transfer function from. So find problem is find transfer function matrix from, it's a vector RS, DS, eta S to transfer function that YS, ES, US. So let us see what is the transfer function matrix in this case. So we need to just write all the equations, the algebraic equation. So first we write that YS, that means here you can see that YS equal to GS into DS, here G, so DS is entering here and another signal is coming here. So this signal is basically CS into ES. So now, so that means GS plus CS into ES. So now here you can see that DS, CS, and what is ES? ES is RS, then negative feedback, so minus. So what is the signal here? The signal is eta S, this signal is entering, minus YS. So that means if you just simplify it, what will you get? That GS DS plus GS CS ES. So this one, okay, so this thing is not needed. So that is GS DS plus GS CS rs plus minus gs cs eta s minus gs cs ys. So then what is ys? If you take this particular term to the left and if you take that common, so then we can write that ys is equal to that gs divided by 1 plus gscs into ds plus that gscs divided by 1 plus gscs into rs, and the last one is minus that gscs divided by 1 plus gscs into eta s. You can also see these things without deriving those algebraic equations directly. You can write, that means this ys and rs, this is that ys and this is that rs. What is the relationship? So you can see that as we have discussed, so this is actually that forward path, so that means gscs in the forward path, and feedback path, this is that feedback path, this is the feedback path, its transfer function is 1, and you have that negative feedback. So that means the forward path transfer function is gscs divided by 1 plus gscs. So that is actually ys divided by rs. So just by looking at the transfer function, looking at the block diagram, directly you can write the transfer function. So here you can see that the first term that you obtain, so that is ys by, sorry, so this one, so that is ys by rs, equal to, you can see here that gscs divided by 1 plus gscs, that you can see directly from just by inspecting the block diagram. So now let us see what are the other transfer functions. That means what is us. So now us is here, that is the control input. So us equal to, you can see here that ds plus this signal. So that signal is, so us equal to the ds plus cs into rs minus the same expressions we are writing, eta s minus cs ys, and if you just replace the ys there, cs eta s, so in place of ys we'll be replacing this expression. So then you will get that gscs 1 plus gscs ds minus gscs so that is cs, again cs 1 plus gscs to rs, and the last term is gscs into cs. Should not write cs square because both of them are that transfer function, so you just write cs into cs eta s, and if you just simplify that one, you will get that 1 by 1 plus gscs ds plus cs 1 plus gscs Rs minus Cs by 1 plus GSCS into eta s. So I am showing it here. That means if you want to find the transfer function just by writing all the algebraic equations, and by simplification you can find it, but the simple procedure is you can see the block diagram and just identifying the forward path and feedback path transfer function, and also what type of feedback you are using, that is negative or positive, then it can be written directly. So in a similar way, you can write that ES. So ES is that error signal. Here you can see ES is that error signal. So ES equal to actually RS minus eta S minus YS. So ES equal to RS minus eta S minus minus YS. So then in a similar way, if you just replace YS, then you will be getting the relationship, that is 1 plus GS CS into RS minus 1 by 1 plus GS CS eta S minus GS 1 plus GS CS ds. So one interesting thing we can notice here, suppose the other signals, that means in this case suppose this RS equal to 0 and eta S equal to 0, that means there is no signal, reference command signal, and noise. So we are interested in suppose to find what is ES by DS. That means the transfer function from disturbance signal to error signal. So where it is? So this is the disturbance signal and this is that error signal. So then we can see from this particular input, from this particular input to that output. So what is the forward path? So forward path would be from here to here. This is that forward path. So you can see that what is the forward path transfer function, that is GS, and as you have that negative sign here, so that means that is minus GS. So forward path is that minus GS here, the minus GS here, and you can see here again the forward path. Then you can see that this is actually that feedback path, only this portion from here to here, this is that feedback path, and here you can see that it is using positive feedback. So now if it is positive feedback, so basically it would be 1 minus, and as the forward path transfer function is minus GS, so then minus minus it would be plus, and you can see that what is the feedback path transfer function, the feedback path transfer function is CS. So that means that is into CS. So minus minus it would be plus, so basically you will be having minus GS by 1 plus GS CS. So without deriving this one, you can just inspecting this block diagram, you can write the transfer function. So only thing is you need to identify which one is forward path and which one is feedback path, and also just see what type of feedback is used in that case. So now if we write all those things, so that means we have that YS here, we have that US here, and another one is ES. So you can see here that we need to find transfer function from RS, GS, eta S to YS, ES, US. So already we have written that expression of YS, ES and US in terms of RS, DS and eta S. So let us write it in matrix form. So if you write it in matrix form, you will get that that is YS. We are writing it in matrix form, eta S and US. So GC, I am just not showing the Laplace variable. So 1 plus GC, and here 1 plus GC minus G by 1 plus GC minus 1 by 1 plus GC, and here you have that C by 1 plus GC, 1 by 1 plus GC minus C by 1 plus GC. So here you have RS, DS and eta S. So you can look at the last equation. So last equation is eta S. So you can see here that eta S equal to RS. So this transfer function into RS. So if you just follow matrix multiplication, that is this transfer function into RS, then minus of this transfer function. So here you can see that minus of this transfer function. So that is actually minus of this one, minus of G by 1 plus GC into DS. So this one, and the last one is this transfer function, minus 1 by 1 plus GC minus 1 by 1 plus GC into eta S. Similarly, I have written the expression YS and US. So now you can see that for this particular block diagram, when you have many inputs and many outputs, so in this case you have 3 inputs and 3 outputs, you can write the transfer function matrix. And if you look at the element of this transfer function matrix, so each element is actually a transfer function. So this is that example. So you need to solve more problems, and my suggestion is, instead of writing all of those algebraic equations, would be easy to write the transfer function or transfer function matrix just by looking at the block diagram. So now we are going to start a new topic, that is that signal flow graph. So signal flow graph is a simplified version of block diagram. It was introduced by J.S. Mason, and it is a cause-effect representation of linear systems modeled by algebraic equations. So let us write that is, this is a new modeling technique, a framework that is called that signal flow graph. Signal flow graph. In abbreviated form, it is also known as SFG, signal flow graph. So this is, it is a simplified version. It is a simplified version of block diagram that we have already discussed. This is the simplified version of block diagram, and it is a cause effect representation of linear systems. So you should remember these things. That means it is applicable to linear systems only, modeled by algebraic equation. So when a linear system is modeled by algebraic equation, then you can represent it in using a signal flow graph. And you all know that whenever a system, dynamical system, is modeled by differential equation just by taking Laplace transform, you can bring that framework into algebraic form. So then you can apply that signal flow graph. And it was introduced by S.J. Mason. So this is a different kind of technique for representing the dynamical systems whenever dynamical systems are modeled in algebraic form. And the most important result of this signal flow graph is that Mason's gain formula. S.J. Mason, he proposed, he has given one formula. Just by using that formula, you can find the transfer function directly if you have that signal flow graph. So in this particular topic, we will be learning how to draw signal flow graph, and from signal flow graph, how we can find the transfer function from one point to other point. But before doing that one, we need to learn some terminologies and some algebraic operations that take place in case of signal flow algebra. So we'll be discussing those things now. So before starting that, again, I want to point out that means it is only applicable to the linear systems, as well as you can draw the signal flow graph whenever it is described in algebraic equation form. So suppose we have one algebraic equation, that is y2 equal to a1 to y1. So now the signal flow graph, so variables are actually represented by nodes. So one variable is y1, another variable is y2 in this particular case. And here the signal is flowing from y1 to y2. So then you can see that y2 equal to a2 into y1. So this is actually that gain. And interestingly, this diagram, this is very important in case of signal flow graph, that this diagram does not imply the relationship y1 equal to 1 by a1 to y2. So this is the mistake we normally do in case of signal flow graph. That means as we have taken the algebraic equation form of the dynamical systems, we have one algebraic equation like y2 equal to a1 to y2 equal to a1 to into y1, and then we can say that okay, so y1 would be equal to, say y1 would be equal to just by dividing that gain y2. But this particular representation is not valid in this case. The reason is, you can see the signal flow graph, it is showing that the signal is flowing from y1 to y2. So along that direction the signal is flowing. So but there is no signal which is flowing from y2 to y1. So there is no signal flowing from y2 to y1. So if you represent that y1 equal to a12, if you go with this particular representation, so then it implies that it would be that y2 here, then 1 by a1 to y1. But this particular representation, this particular signal flow graph does not imply it, does not imply this relationship. So in case of signal flow graph, you should not go with that type of operation. You should not go, because this is a wrong description of that system. So signal flow graph actually represents that y in this particular case. So if it is y2 equal to a1 to y1, so signal is flowing only from y1 to y2, and the gain is a12. So that means only this particular algebraic equation holds corresponding to this signal flow graph, but the other one, that means if you divide by that gain, so that relationship does not hold in this particular case. So it is very important. And there are some terminologies. So here in this particular case, we say that U1, Y1 is that input node, and Y2 is output node. So from here also you can understand, that means we are representing a dynamical systems. So in dynamical systems you have some input and you have some output. So if you just take this type of description, so as Y2 is output and Y1 is input node, so if you write that Y2 equal to 1 by A12 into Y1, so that means you are indicating that signal is flowing from output to input, which is wrong. So that's why in case of signal flow graph, you should not go with that division by that gain. So now here you can see that the variables. So here two variables are there, input variable and output variables. So variables are represented by nodes, and A12 is gain. And here the branch from Y1 to Y2. So that means from Y1 to Y2. So this is one branch, and that branch gain is A12. And as I have pointed out here, the signal, this is very important, that signal flows along the direction of arrow only. So that means in signal flow graph, whenever you just represent two nodes and two nodes are connected via one branch, and then just by writing this A12, that means it indicates that this is the gain in that branch. And the most important thing is this arrow symbol. This arrow symbol indicates that signal is flowing from Y1 to Y2. The reverse is not valid in this particular signal flow graph. So let us take one example, that is suppose one system is described by the signal flow graph, that is Y1 and A32 Y3, and then Y3 equal to A23 Y2 and A43 Y4. So here you can see that the system is described by a set of algebraic equations. So whenever it is described by a set of algebraic equations, then you can represent it using signal flow graph. A34 Y3, then A44 Y4, and another one is Y5 equal to A25 Y2 plus A45 Y4. So we'll be drawing the signal flow graph corresponding to this set of algebraic equations. So we can see that how many variables are there. So there are 5 variables. Here you can see the 5 variables, that is Y1, that is Y1, Y2, Y3, Y4 and Y5. So let us put that 5 variables, that is y1, this is y1, this is y2, and this is y3, y4, and y5. So these are the 5 nodes. Then what is y2? Just concentrate on this particular algebraic equation. So y2 equal to a12 into y1. So a12 into y1 means there is a path here. So this path is gain is a12, and there is another term here, that is y3. So another term is here, signal is flowing along that direction, that is a32. So you can see that y2 here, y2 equal to a12 into y1 and a32 into y3. So that means that first algebraic equation is represented in signal flow graph by signal flow graph. So now let us see what is y3. So what is y3 here? y3, so y3 equal to a23 into y. So that is a23 into y2, so this term, and another one is a43 into y4. So that is a43 into y4. So that means this equation is represented by this part of signal flow graphs. And then look at the third one. So third one is, that is y4 equal to a24 into y2. So that means there would be a branch from here, that is a24 into y4, and then so this first term is done. The second term is a32 into y3. So that means there will be another branch here, that is a34 into y3, and the last one is a44 into y4. That means it has the self loop here, that is a44 is that gain. And so this particular algebraic equation is represented by that part of the signal flow graph. And the last one is y5. So y5 equal to a25 into y2. So a25 into y2 means there would be a branch, signal is flowing along that direction. So do not forget to give that arrow direction, because it indicates from which node to which node the signal is flowing. So this is very important in signal flow graph. So do not forget to give that arrowhead, because without arrow symbol signal flow graph does not make sense. And then the last one is that a45 into y4. So that means there is a branch here, this is a45. So that means this is that signal flow graph corresponding to this set of algebraic equation. And from here you can see that how to represent a set of algebraic equations in the form of signal flow graph. So here we can see that this is that y1, this is that node, and this is actually that input node, and this is that node which is that output node. And you can see that signal starts flowing from this particular point to this point. So here we can just mention some terminologies like that. Input node. So which node is said to be input node? It has only outgoing branches. It has only outgoing branches. So in this case the input node is y1. Here you can see that y1, this one, that is that input node, it has only one outgoing branches. And in case of output node, there should not be any outgoing branches, all the incoming branches. You can see that this is incoming branch, this is incoming branch. So in case of output node, it has only incoming branches. It has only incoming branches. So in the above signal flow graph, you can see that Y5 is the output node. Now there is one interesting thing. That means we can make any node, any non-input node as output node. Let us see what is that. We can make any non-input node as output node. So if you see this particular signal flow graph, here you can see that this is that input node and this is that output node. So Y2, Y3, Y4, they are not input node. So according to this statement, what we can do, we can make any node, that means which is not input node, that is Y2, Y3 and Y4, we can make it as output node. So let us see how it can be done. So suppose you have one signal flow graph like this. Say in this case, suppose this is Y1, Y2, Y3 and Y4. So suppose signal is flowing like this, and so suppose this is that signal flow graph you have. So now in this case, the input node is this one, input node, this is that input node and this is that output node. So then according to this statement, we can make any non-input nodes. So any non-input nodes means here you have Y2 and Y3. So we can make those nodes as output node. How? So we can write that, okay, so this is Y2 and this is Y3 and signal is flowing like this and gain is 1. So if gain is 1, we can just write here that Y2 equal to Y2, just applying that signal flow graph algebra. Y2 equal to just Y2 because here signal is flowing from this direction to that direction. So we can say that this is that output node because it has only the incoming branch. Similarly, we can write that Y3 equal to Y3 according to the signal flow algebra. So here you see this is that incoming branch. So this is that node where you have only incoming branch. So that means that would be one output node. So that's why this is that statement. We can make any non-input node as output node. So now what happens in case of input node? So another statement is we cannot, this is very important, we cannot make any node as input node. So this is very interesting and important in signal flow graph. So here we have seen that any input node, non-input node can be made as output node, but in this case we'll see that we cannot do the same thing in case of input node. Let us see. So first we take one example. So suppose you have one signal flow graph here, that is Y1, this is Y2, this one. So signal is flowing like this, and suppose you have one branch, so that is A23 and A12. So now this is that input in this particular case. So suppose this is that input, input node. So now suppose we want to make this particular node as input node. So input node means if we just make it here, so suppose this is one node and this node is suppose y2, because our objective is to make this y2 as input node. Just like output node, if we make it for input, then what happens? You can see here that using that signal flow graph algebra, what you had initially that y2 equal to so suppose this is 1 again, so y2 equal to y1 plus a23, here you had y3. So before adding this branch, we had this algebraic equation. So now once we add this branch, that means if we follow the same technique what we have done in case of output node, if we do this one, then what happens? That means whenever this branch is added to this signal flow graph, according to the signal flow algebra, if you just look at that particular node, so then we have y2 equal to, you see, y1 plus this one, that is a23 y3 plus this one is there, so that is y2, here gain is 1. So now you can see that this particular algebraic equation and this particular algebraic equation, they are not same. So that means if you want to make a node as input node, just like output node what you have done here, you cannot make this. So this is very important, you cannot make this. So that means in case of signal flow algebra, whenever you have a signal flow graph, any non-input node can be made as output node, but it is not possible for input node. That means any node cannot be made as input node. So now let us see some terminology that we'll be using in signal flow graph. One is that path. A path is any collection of a continuous succession of branches traversed in the same direction. So a path is any collection of a continuous succession of branches traversed in the same direction. So let us see in this particular example what is that path. So one path is you can see that y2, y3 and y2. So one path is y2, y3 and y2. So that means y2, y3 and y2. So this is one path. Another path is y3, y4, y3, y3, y4, y3. So this is another path. Another path is y2, 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 y3, y4, then again y3 and y2. So in this case, you can see that this particular y3 node is used twice. So it does not prevent any node from being traversed more than once. So that means in this particular signal flow graph, so what we have that path y2, y3, y2. So this is one path. Another path is y3, y4 and y3. Another path is y2, y3, y4, y3, y2. So for this particular path, you can just take that note. That means it does not prevent any node. So in this particular case, that node y3, any node from being traversed more than once. So this is the definition of path. So the next definition is that forward path. A forward path is a path that starts at an input node and ends at an output node, and along which no node is traversed more than once. Very important. That is a forward path. A forward path is a path that starts at an input node and ends at an output node. So it starts at input node and ends at output node, not any arbitrary in between any arbitrary nodes, and along which no node, this is the difference with that path, no node is traversed more than one. So that means a forward path is a path that starts at an input node and ends at an output node, and along which no node is traversed more than once. So let us see in this particular example what we have. In this particular example, you can see that this is actually that input node and this is that output node. So one forward path is y1, y2, y5. So you can see here that this is that path, this one, and that one. So this is one forward path. And another forward path is y1, y2, then y4. Here you can see this is that part, y4 and y5. The another path is forward path is y1, y2, then y3, this path y3, then again y4, and y5. So in this particular signal flow graph, you have three forward paths. So three forward paths are there. So those are y1, y2, y5. Another forward path is y1, y2, y4 and y5, and another one is y1, y2, y3, y4, y5. So here you can see that means no node is traversed more than once. From this particular example you can see, but this is different from the path. So what we have discussed today. So today actually we have solved two examples from block diagram representation, and the second example shows that how to find the transfer function matrix. And then we have started that signal flow graph. The most important thing is whenever the system is described in algebraic form, then you can represent it in signal flow graph framework. And the most important one is you cannot just use this type of representation. The reason is in signal flow graph, the arrowhead shows that the signal is flowing from one node to other node, and if you take the reverse one, it does not make sense. And then we have taken one example, that means a set of algebraic equation, how they can be represented by a signal flow graph. And we have started discussing some terminologies, and here we have shown that any non-input node can be made as output node, but it does not hold for input node. And we have discussed that path and forward path. So next class we will be discussing the other terminologies like loop, path gain, and non-touching loops. Thank you.